Hi everyone! In this lecture we're going to focus on some selected material from chapter 12 of our text. In this chapter we're looking at problem solving and reasoning. So first let's define what a problem actually is. We can say it's an obstacle between our present state and a goal state that we want to get to. Now, it's not immediately obvious how we get around the obstacle that's in our way, and typically we say problems are difficult. Now, we can look at it from a Gestalt approach about how to solve a problem. So we could look at how we represent a problem in our mind. So here we have an example of a crossword puzzle. It's likely that when we're trying to solve something like this, that we restructure the problem, or essentially change how the problem is represented to us. So this particular problem is arranged in this fashion. We can see all the white blocks or spaces for letters, and we have, ones across and one down. But typically when we're solving this, now different people will solve this different ways or restructure it or represent it in their mind in different ways. But for example, somebody might just represent small sections of the problem in their mind as they're trying to solve it. So again, the idea is with problems from a Gestalt approach is that we tend to restructure the problem in a way in which we can represent it in our mind and kind of get us closer to overcoming the obstacle of the problem. And another example I'll give you is Kohler's circle problem, and we'll take a look at that on the next slide. So this is the circle problem that I mentioned on the last slide. Now this full problem is laid out in your text, and you can actually work this problem out if you'd like to. But the idea is that this problem can be very difficult to solve until you change how it's represented. Now you see the circle, and you see the crosshairs here, and you see a triangle. Now when this problem becomes easier to solve is when you recognize that this right here is actually forming a rectangle, and the line here that's marked with the X is actually the diagonal crossing through the middle of the rectangle. That's when this problem becomes easier to solve. But it's not until you kind of change how you're representing the problem or seeing the problem that you can see the solution to the issue here. Now, we can look at insight into problem solving. Now, basically, when we have an insight when we're solving a problem, we're saying that it's insight because basically you're trying to solve a problem and you have a sudden realization of what the solution is. So you're working along with the problem and you really don't know how close you are to the solution, if you're close at all, and then suddenly you just have the answer, you get it. Now, often this requires some restructuring of the problem in order to have this insight or aha moment. Here we have a study that looked at insight and problem solving. So this was done in '87, and they gave participants insight problems like the triangle problem and the chain problem, and we'll look at those problems on the next slide. They also gave participants non-insight problems. So these are problems that basically you work through gradually and you eventually get to the answer. So there's no aha moment, like you're working through the problem and then all of a sudden you just get the answer. For example, things like algebra don't work that way. If you've had algebra, I'm sure most all of you have, you know that when you're working an algebra problem, it takes a while and you have steps to go through and you gradually get to the answer. There is no aha moment involved here. So two different types of problems, insight and non-insight problems. And they asked participants to give warmth judgments about how close to the solution they were to the problem. So every 15 seconds, they asked the participants to rate how warm they felt towards how close they were to getting a solution to the problem. This was done on a 7-point scale, 1 being very cold or very far away from the answer, 7 being the hottest rating or being very close to the answer. So here we're taking a look at those two insight problems. So we have the triangle problem in figure A, portion A of this figure, and then in portion B we have the chain problem. So in figure A, the goal is to essentially get this point here to the bottom portion here. So essentially flipping the whole figure around. So the point, this figure is basically flipped downward. So the triangle is down. And that requires moving this whole point essentially downward. Now, the participants only allowed to move 3 of the dots in order to do this. And in the chain problem, basically they're told that a woman has 4 pieces of chain that are represented here. And in order, basically the goal is to link them all together. But in order to open a link of the chain, it requires 2 cents. And to close a link in the chain is 3 cents. And she only has 15 cents total. Now, these type of problems tend to be the type of problems that participants struggle with for a bit. They have to restructure, kind of rework, but then all of a sudden they get the answer. It's definitely one of those aha moment type of problems. Now, what they found in this particular study is that insight problems were solved very suddenly. That is, participants were struggling along, kind of trying to work them out, and then all of a sudden they had the answer. But non-insight problems, like the algebra problems, for example, were solved much more gradually. So for graphing the results here, it looks something like this. So this is the median warmth rating right here as a function of time before solution. Now, if we notice here the algebra problem, you see that this is, again, warmth rating. Participants are saying that, it's very gradual. Their warmth rating is getting higher and higher. Whereas with the insight problem, notice that it's saying pretty much the same, and then all of a sudden just shoots up very quickly. This is that insight that we're talking about, kind of that aha moment occurring here. Now, if we focus on some obstacles to problem solving, so things that make it harder for us to solve a problem, one would be functional fixedness. And this occurs when we have an object, for example, and we're very familiar with the functions of that object, so what it does, but we tend to restrict the object to those functions, basically thinking that the object is not good for anything else. For example, in your book, it talks about the candle problem. And the issue here is that participants tend to see the candle boxes as just being containers for the candles and basically not thinking about them as being used for anything else. And in this particular problem, the candle boxes need to be used as supports. That's the solution. But seeing them as only containers for candles kind of limits participants in their ability to see them as being used for supports, or slows them down to getting to that solution. Another one your book focuses on is the two-spring problem. So basically the idea here is that there are pliers in the picture, so the participant can use the pliers to weight one of the strings down. But they see the pliers as being basically just a singular function, and they don't see them as being used as a kind of a weight, which is the solution to the problem. So again, this is that idea that we restrict an object only to the functions that we're familiar with it being able to perform, and we don't think about objects being able to be used in different ways. Kind of similar in a way is this idea of mental set. So this is kind of a preconceived notion we might have about how to approach a problem. So we kind of already have an idea of how to approach a problem, and because of that, we don't see novel ways to approach a problem that might actually work better. So this, of course, would be based on a person's past experiences with a problem or similar problems like this. The book talks about a water jug problem. Basically, this is kind of showing how this given mental set inhibits participants from using a much simpler solution. And here we're looking at the water jug problem. So we have different problems here. So we have 8 total problems, and we have 3 different jugs containing liquid in quarts. And we have how much each jug contains per given problem and the desired quantity that we want to get to. So participants have been exposed to a fair number of these problems before, and here we're taking a look at finding the solution to the first one here. Now, basically, the participants would start out with B minus A, and then B minus A minus C, and finally get to the answer with B minus A minus 2C. Now, there are more efficient ways to get to this particular answer, but what they found was that previous exposure to this type of problem kind of gave participants a mental set about how to go about solving this problem. So this is kind of why participants were taking a little bit longer to solve it, because they were kind of persisting with this earlier idea of how to solve the problem rather than seeing the easier solution. Now, when we tend to represent a problem or think about a problem, we essentially are kind of using this idea of a problem space. So this was proposed by Newell and Simon, and they kind of proposed that a problem space consists of 3 different states. So our initial state, where we are now, our goal state, where we want to go, and an intermediate state or states, depending on how many steps we need to take to get to our solution or goal state. Now, a good example of this type of problem is the Tower of Hanoi problem. We'll take a look at that on the next slide. But basically, with the Tower of Hanoi, we have operators. So these are specific rules in which moves are allowed in this problem and moves that are not allowed. Now here we have the Tower of Hanoi. We have our initial state on the left here and our goal state on the right. And here we have a list of operators. So essentially we can only move one disk at a time. We can't have any smaller disks on top of underneath larger disks. So this larger disk here can't go on top of the smaller disk, for example. So these are just a couple of examples of the operators or rules of the Tower of Hanoi problem. Now, in order to kind of perform something like the Tower of Hanoi, if we're trying to keep it down to a limited number of moves in order to solve the problem, we kind of have to do a means-end type of analysis. So this is trying to reduce the difference between our initial and goal states. So essentially, we do this by creating sub-goals or creating intermediate states that are closer to the goal, kind of trying to plan out what we're going to do before we do it, so we don't take any unnecessary steps or make unnecessary mistakes. So here's just kind of an example of how we might solve the Tower of Hanoi problem by using these intermediate states as kind of a cue to help us solve this problem without making unnecessary mistakes or using an unnecessary number of moves to solve the problem. Now we kind of focus on how the problem is stated, and as you can imagine, it is quite important how a problem is stated in that it can affect how a person will try to solve the problem. Now, this is one you can also see in your text. This is the mutilated checkerboard problem. Now, the conditions given to the participants differed in how much information were provided about the squares involved in the checkerboard. And it's easier to solve when information is provided that points toward the correct representation of the problem. Meaning that if information given kind of tells participants how they maybe should represent the problem when they're trying to solve it, it will be much easier for them to solve than if they're not given that same information. Here we're taking a look at an example of the mutilated checkerboard. So basically they give participants a domino here, which of course is the size of 2 checkers, and they remove 2 corners of the board. Now, participants were broken up into groups. So one group got a board like this, but all the spaces were white. So basically there is no color cueing here at all. It's just white checks on this board. Another group got color, much like this one, except it was pink and black. And some groups got words on the different blocks here. So one group got pink, red, pink, red text. And then the last group got bread, butter, bread, butter, bread, butter. And basically what they found was that when participants were given the word condition, it was easier for them to solve this problem. Now, even though only 2 spaces have been removed, and there are 64 spaces total, and this is consisting of 2 here, 2 spaces. Just mathematically, it seems as though it would be possible to cover every space on the board with these blocks, but it's actually not possible because of the corners that have been removed. And this is easier to see when this is represented by words. Or even by color, but the worst group, as you might imagine, was the group that had no cueing at all. So no words, no color, just given the whiteboard. They were the ones that struggled the most because they're not really getting any kind of insight into how to solve this problem in terms of how to represent it. So again, the word condition seemed to be kind of working better for participants. And also used in this particular study was this idea of think aloud protocols, so allowing participants to say aloud what they're thinking. And it kind of shifts, there's kind of a shift here involved in how one perceives the elements of the problem. So as a person's talking out the problem, it tends to kind of change their perception of the problem and kind of get them going toward the right direction to solve the problem. So here we take a look at how we use analogies to solve a problem. So this is how we're using a solution we've gotten on a previous problem, which is similar to our target problem, and we use that logic to kind of get us to the solution of our target problem. So we can use the arrest and marriage problem, which is detailed in your text, as our source problem, and use that solution and the logic of how we got to that solution to help us solve the target problem or current problem of the mutilated checkerboard. So the Russian marriage problem goes like this. There's a small Russian village, and there are 32 bachelors and 32 single women. The village matchmaker has made out of these bachelors and single women 32 heterosexual satisfactory marriages. But one night, 2 men challenge each other to an eating contest and die. So now there are 30 bachelors and 32 single women. Can the matchmaker come up with 31 heterosexual marriages among the 62 survivors? And of course, the obvious answer is no, because there are an uneven number of males to females. Now, it's very obvious what the answer to this problem is, but it's not as obvious with the mutilated checkerboard, even though the logic is very, very similar. And that with the mutilated checkerboard, you have 64 total blocks like you do in the Russian marriage problem. You have 32 bachelors and 32 single women, which is 64 total, just like the checkerboard. But if you remove two of the same checks from the checkerboard, which is what you do in the mutilated checkerboard, then it stands to reason that, much like the Russian marriage problem, it's not possible to make 31 perfect matches between two different blocks. So essentially, male-female marriages in the Russian marriage problem, or in the mutilated checkerboard, for example, in the pink-black condition, pink-black matches across the board because you don't have an even number anymore. Okay. Now, people who get the Russian marriage problem first tend to solve the mutilated checkerboard problem faster. Now, this is again that idea of analogical problem solving. So you're kind of taking this solution or idea of how you solve the problem, the logic that you used, and you're transferring it from one problem to another. So we're going from the source problem to the target problem. So this logic used in the Russian marriage problem can help us solve the checkerboard problem faster. Now, in order to do this, first we have to notice the relationship. If we do the Russian marriage problem and then do the checkerboard problem and we don't notice the relationship between the two, then that's not helpful. We have to notice the relationship between the two, and we have to map the correspondence between the source problem and the target problem, and then we have to actually apply that mapping. So we have to actually apply the logic from the first problem to the second problem in order to solve it. Now, an example of a study that was done using this idea of analogies and kind of studying whether or not people could actually do it was this particular one involving this radiation problem. So essentially, often hints must be given in order to notice the connection between the two problems that are being worked on. And what we find is that surface features tend to get in the way. So the details of stories tend to get in the way of people seeing the actual structural features. So the logic essentially behind solving the problem. The surface features kind of get in the way, and people have a harder time seeing the structural similarity between the two problems. But people who do see it tend to get a lot of help out of this ability to use an analogy from a previously solved problem and kind of map it on to a new problem. Here are the two different problems that participants in this study had to work on. So the first one is actually in figure C here. So this is the fortress problem. So the idea here is that this army is trying to get into this castle, and they've tried to attack it from all sides, and it's not been successful. So then they finally divide the army into small groups and attack from all sides at once, and that works. So attacking from all sides and using a smaller amount of force on each side is actually the solution to getting into the castle. So once participants solve that, they then work on the radiation problem. So the idea here is that they need to attack a tumor with radiation, but there's all kinds of rules about the strength of radiation they can use and the different directions in which they can't go, or if they do this, then they're going to hit this organ. Basically, the idea here, though, is that the solution to the problem is the same as it really is in the fortress problem. That is to use smaller amounts of radiation and break it up and hit the tumor from all different directions. That's the solution to the problem. And what they found was that of all the participants, only about 30% actually noticed the similarity, structural similarity of the two stories, and were actually able to use the solution or the logic they used to solve this problem and map it onto this problem. Of the other 70%, they just got caught up in the surface details of the stories and just didn't notice the similarity, and it took them longer to solve the problem. So again, this is that idea that in order to be able to use analogy, you must notice the similarity between the structure of each story, and you must be able to map that logic on from the source problem, which is the fortress problem here, onto the target problem, which is the radiation problem. Now, how do we get people to be better about noticing the similarities between stories and being able to use analogy? Well, one thing we can do is make the similarities between the stories or problems on the surface more similar. So people won't get as caught up in surface differences between the problems and can actually notice the similarity. So that's one thing we can do, is just increase the surface similarity. And again, the surface features are, again, it's just this idea of the specific elements of a given problem, so the details. We can also make structural features more obvious, so the real bones of the story, the logic behind the story, the important part that helps you solve the new problem, we can make those more obvious. And again, that's really what's governing the problem. And that's the important part for people to notice. But again, the idea is that people are getting more caught up here in the surface features. So this is just two ways in which we can help people out. Give more surface similarities. So make these match up more between the two stories. But also make these structural features that much more obvious as well. So people might be more likely to notice. Now let's take a look at expert problem solvers. So as we know, there are experts in pretty much every area of study. So first, what is an expert? So we could say formally, this is a person who has devoted a very large amount of time learning about a field and practicing and applying what they've learned and becoming extremely knowledgeable or skilled in that field. Now, experts solve problems in their field faster and with a higher success rate than beginners. So this is kind of behavioral evidence that we can gain from experts versus novices, in that experts are going to solve a problem faster and they're going to have a higher success rate than beginners. Now, note that this is within their own field. And of course, this stands to reason because experts should possess more knowledge about their field. Now, how do experts solve problems? Well, first they take knowledge and they can organize it so it can be accessed when they need to problem solve. So they've had more experience with all of this information, but then they also have it organized in such a way that they can readily access it when they need it. And just keep in mind here, with their particular field, experts tend to focus more on structural features, whereas novices or beginners tend to focus again more on surface features or details, which are kind of distracting from the actual bones of the problem. Also, we see experts spend more time actually analyzing the problem. But again, what's important to note is that experts are no better than beginners or novices when they're given problems outside of their field. So this ability to problem solve within their field does not generalize to other areas or other fields of knowledge where they're not experts. Now, this is something that's very interesting in that when we're looking at creativity, which is this next portion that we're going to focus on, experts tend to be less likely to be open to new ways of looking at a problem because they've had so much experience and so much time in this particular field. They're going to be less likely to look at new ways of problem solving. Now, that's kind of how we define creative problem solving, or creativity, is this idea of innovative thinking, or new ways of thinking, new ideas, forming new connections between existing ideas. Also just divergent thinking, so open-ended thinking, using a large number of potential solutions. Oddly enough, we see a lot of innovations coming out of psychology, but also every other field too, by young researchers, because they're looking at different topics of areas of study in a new way. Whereas people who've spent their whole lives, who have been, in the field for years, looking at certain things, they're less likely to look at things from these newer perspectives, just because they've had so much experience and they're expert at this point. Last, we look at creative cognition. So this is the idea that we can actually train people to think creatively. And this was done by Fink. And he would blindfold people and have them randomly select like 3 items from a page. And then mentally he would tell them to create a novel object using those 3 items. So a brand new object that doesn't exist. And he called these objects that they created pre-inventive forms, because the ideas behind these objects essentially existed before they were created. And here on this page, we take a look at some of the objects that people created. So they would have to name them after they actually created them. And again, these are things that don't technically exist. And what he found was that even people, who wouldn't normally be thought of as being creative, tended to be more creative with more experience with this. People tended to do well with this type of problem solving. And I think the idea here is that, according to Fink anyway, you don't have to be an inventor to be inventive. You don't have to be an inventor to be creative. You just have to be given kind of the opportunity and the guidance to do it. Now, as always, make sure to look through your text carefully in this chapter, and I'll be back with you next week with our final chapter, Chapter 13. Have a great week.